Okay, so that's k-means clustering. Now let's see how that can be used for image segmentation. And basically, this is just one slide I have, and you have seen like how simple that k-means algorithm is, and now you will see like how simple this SLIC algorithm is. So this was proposed in 2012, and so the idea is you will use this k-means clustering over images, and the pixels of the images will be your sample points. Okay, so for example, if you have like, let's say 300 cross 300 image, so you will have that many pixels, and basically each pixel is your data point. And what you're going to do is you're going to use some kind of properties of that pixel, and basically it could be like the RGB color. All right, so those three values, and it could be the location of that pixel, where exactly that pixel is located in this image. Okay, so we use those 5 different values. So in this case, your feature vector is 5-dimensional, R, G, B, and then X and Y. XY is for the position of the pixel, RGB is for the color component. And later you will see we don't use RGB color space. We use like a different lab color space, which is fine. You can use any other color space as well, HSV or something else. But the idea is to use the appearance. Okay, so then each pixel is represented using this feature vector, which is 5-dimensional long. And then we just run this k-means clustering using those data points. Now, one interesting question to ask is, what is the role of number of cluster centers? Now, the number of cluster centers will determine how many segments you will get in your segmented image. For example, if you set your number of cluster centers to 1000, then you're going to get 1000 different segments in that image. Okay, which could be something like this on the top left, right? And as you keep reducing the number of cluster centers, you can see that your segments are actually getting bigger and fewer in number. And as you go down, you can see like this is even like coarser, so your segments are much bigger. And you can see like how clean these results are. And that's one of the reasons like this algorithm is still used today for like a lot of applications. And we are using this for, I think, several of our research projects as well. So it's very simple algorithm, very efficient, gives you very good results. Okay, so this is like the input is an image, the algorithm is k-means, and this is going to be your output. Now let's see step by step like how this kind of output can be generated. What we do, we first of all initialize the cluster centers. So that's the first step for a k-means algorithm. Okay. And the way we do it is we divide your image into like multiple grids depending upon how many cluster centers you want. For example, if you want 100 different cluster centers, you will create a grid of 10 cross 10. And then within each grid cell, you will randomly pick one of the pixel as a cluster center. Okay. And as I said earlier, you will have a 5-dimensional feature vector. You will have 3 for colors and XY for position. We need position because it may happen that, for example, like pixel over here, if it's like very dark pixel, the values might be 0, 0, and 0. Similarly, the pixels over here, they are also 0, 0, 0. If we just use color, they will be clustered together, but there's no way they are like the same segment, right? They're far apart in the image. And that's why we need like this position value as a feature. Okay, we want like pixels which are close to each other as one segment. Okay, so the second step, and again, this is ideally not required. It's just again a heuristic. Even if you skip this, it's not going to change like a lot in terms of result. And the idea is we first try to compute like the gradient of the image, and whatever cluster center we have initialized, we move it to a location where we have the smallest gradient. Okay, so let's try to understand why this step is required. As I said, I mean, for some images, it might like change the performance, but most of the times it won't do a lot. Okay, but let's try to understand the intuition. So you have seen that when you compute gradients in your image, then if there is a high gradient, it means that the color values might be changing a lot, right? So that might be an edge. And that's what you use for your edge detection algorithm. So if gradient is high, then if it's an edge, which means that you are at a boundary of like two different segments. And that's not like a good initialization, because then you don't know like which way to go. And that's why what we do is we simply shift the cluster centers to like a smallest gradient. And if the gradient is low, we know that, okay, it's not an edge and it might be like a same segment. Okay, so we just try to move towards the center of the segment. So that's the second step, and it's just done once. So again, the first step is done once, then this is also once. Then this is like the iteration for the k-means algorithm, which will be repeated again and again to refine the results. Okay, so again, this is like the traditional like step which we do for k-means clustering. What we will do is we will compute like the cluster assignment. So for each pixel location, we will compute the distance using these set of features, which are 5 different values. And we will use that distance to actually assign the cluster center. Okay, so this is the cluster assignment. And then again, what we will do is we will recompute the center of the cluster, right, based on the new assignments we have. And that will shift your cluster center. Okay, so these are the two traditional steps in k-means. We just keep repeating those two steps until we can have like some kind of stopping criteria, whether we want to stop after 10 iteration, 20 iteration, or we can stop like when the cluster centers are not changing. And at the end, you will get like this nice quality result. And you can see that these segments are solely based on the color value, right? And also like if they're close to each other, they are actually grouped into the same segment. One thing you will notice is two segments which are close to each other, even if the colors are similar, they are actually separate cluster centers. And the reason is because distance also plays a role. And you can see like most of the time, you will see like a straight line dividing those two segments. Okay. And if you want to relate that to I think one of the algorithm which we discussed, the k nearest neighbor algorithm, right? How the decision boundary looks like. So these straight lines actually explain like those decision boundaries. So this will happen only where like you have uniform color, not for like other locations where there's some gradient or something. Okay, so I think some interesting properties about this algorithm, it's pretty fast to run, even for like images of this resolution. It can be like done in fraction of seconds. And that's why it's used for like in a lot of real-time applications. If you need like regular superpixels, it's very useful. So these segments are actually called superpixels. Okay. Now, some of the downsides, like you might miss some of the thin objects. Because if you think about this, color is a factor which is playing an important role when you're creating these clusters, but then distance is also important. So because of distance, most of the time you will see that the segments are actually rounded shaped, right? Because that will make it uniform. And that's why like if your objects are like have thin shape, they will be ignored. So to take that into account, what you can do is when you're computing the distance between like the cluster center and the pixel point, you can actually assign some kind of weights to colors and position. Okay, so let's say you want to pay less attention to the distance, more attention to the color, then it may happen that, okay, your segments will not be like rounded shape. Then you will get like all odd kind of shapes as well.